I aim to, one, show you the context of my PhD and placement work, two, introduce you to data at the Brilliant Club, and three, excite you about the power of data in university access. Most of my PhD time is spent on particle physics research. And the main thing I do here is some machine learning to classify a rare process that we're interested in and classify this against much more common background processes that aren't as interesting to us. And I do this mainly using deep neural networks, one of which I'm showing on the right here. I also spend a significant amount of time doing particle physics education work. And the main avenue through which I do this is called Atlas Open Data. Our aim is to provide real data for education worldwide, and namely like data science, machine learning sort of education, with the context being particle physics data. If you fancy, you can have a look at the website, opendata.atlas.cern. I'd be interested if you want to have a look, if you let me know what you think about it or whatever. DiskNet has already been mentioned by Pete. Data Intensive Science Center in the Southeast Physics Network. And the tagline for it is that the students on it are being given world-class skills for handling huge data volumes, rates, and complexity. And the main benefit I see from this PhD is that we get to do these 3-month internships tackling any manner of data science project. Could be at companies, charities, public sector, non-profits, et cetera, as people are saying. And always interested in more placements. You just need to email Michelle here, m.limber@soton.ac.uk. She'd be very interested to have a chat about what you might have in mind. The first placement I did after my first year was at the NHS. That was super cool. The main thing I was doing here was natural language processing, or NLP, to try and implement a drop-down menu of the most common doctors' diagnoses so that they could save some time and thus money compared to having to write out the full diagnosis. I was trying to find the top 10 like categories of most common diagnoses, such that someone could then make a drop-down menu with those top 10. And if it was something else, there would be another option, and only then would they have to type. This was some of the like categories that I came up with. If I'd done this not so long ago, I might remember what all of these words mean, but I think it's something to do with old people, right? UTIs, falls, and delirium. I can't remember what those two words mean. And then I was also trying to kind of find out where in the hospital these were happening. AMU, can't remember what MOC stands for. And like the speciality of the part of the hospital it was in. That was super cool, and that could in itself be a separate presentation. But today I'm talking about my work at the Brilliant Club. So I wanted to kind of compare and contrast what I do most of the time in my PhD compared to what I did at the Brilliant Club. I like to think of it as it was different data, but using the same principles. And I'm sure that would be the case for other PhD students if you were to host them in an internship, for example. So in particle physics, I analyze about tens of millions of records at a time, whereas in the Brilliant Club, I was analyzing about 70,000 records at a time. In particle physics, we have particle level data, like the energy or the speed of individual particles. And I kind of saw a parallel in this as pupil level data, such as whether they're on free school meals. We also have in particle physics collision level data, like the number of electrons in each collision. And I saw a parallel in this at the Brilliant Club in terms of placement level data, such as the number of pupils on a placement that had no parental history of higher education. In particle physics, when we have missing data, we tend to just discard that whole collision because there are just so many collisions that we can afford to do that. But at the Brilliant Club, I had to find ways to deal with missing data. So that was a nice bit of difference for me, a nice challenge. So I learned things as well. So now moving on to the second part, introducing you to data at the Brilliant Club. So the problem we're trying to address at the Brilliant Club is rather simple. It's that right now, students from the least advantaged backgrounds have a 1 in 50 chance of accessing the most competitive universities compared to 1 in 4 of the most advantaged students. This means that disadvantaged students are 18 times more likely to miss out on life-changing higher education. This disadvantage doesn't disappear when they enter university. Disadvantaged students are 3 times more likely to miss out on a first or 2-1 grade at the end of university, which affects an individual beyond their time at university and impacts society as a whole. So we know that graduates from the most competitive universities are more likely to access professional careers and have higher rates of life satisfaction. One stat is that on average, they'll earn £10,000 more than their peers. So hopefully you agree that it's fundamentally unfair that some people get a higher chance of achieving this than others. So that's where the Brilliant Club comes in. It's got a simple mission to increase the number of pupils from underrepresented backgrounds that progress to highly selective universities. And the particular way the Brilliant Club has of tackling this is to mobilize the PhD community to share its expertise with state school students. In pursuit of this mission, we at the Brilliant Club run 2 complementary programs. The first one is called the Scholars Program, and that places researchers such as me, a PhD researcher, as part-time tutors in schools to deliver university-style tutorials based on their academic research. So, for example, I deliver courses on my particle physics research, and this isn't just PhD researchers. Postdocs as well can do this, or people who used to research can do it as well. And there's also the Brilliant Tutoring Program, which supports the national post-COVID tutoring effort so that pupils can access a future they deserve. This program re-engages and rebuilds pupils' confidence in core subjects, maths, English, science, etc., by working with subject expert tutors. So, for example, I would run some catch-up lessons based on the curriculum in physics, for example. The rest of my presentation focuses on this top one because that's the one that had most data. This has been going on for less time. And this one, just like to point out, is available for master's students to be tutors as well. We as a Brilliant Club work in every nation and region of the UK. In the last academic year, 2020 to 21, worked with 948 schools, 182 of which were in social mobility cold spots, basically regions that don't have much movement of the people that were in them towards cities or areas in which there are universities, for example, and 267 of which were in rural or coastal areas, which historically have less progression to university. Worked with more than 25,000 students across our programs, 42 partner universities, and over 1,200 postgrad researchers delivering these programs. The Brilliant Club has just set out a brand new strategy for 2021 going to 26, and it sets out our ambitious plans for the next 5 years, those 5 years. The plans are to work with 100,000 students to take part in the Scholars Programme by 2026, the Scholars Programme being that one where PhD tutors are teaching courses based on their research, leading to 30,000 graduates of the Scholars Programme entering one of the most competitive universities by 2034, leading to 1 in 10 state school students that are entering the most competitive universities by the end of this decade, so 2030, will be graduates of the Scholars Programme. In this slide, I aim to show you the impact of our programs and demonstrate how they're designed to support progression to highly selective universities. If I take just as an example figure, 100 pupils that have completed the Scholars Programme, or in other words, you can think of it as a percentage, 79% of them applied to a highly selective university, 77% received an offer from a highly selective university, and 56% progressed to a highly selective university. Comparing this to a control group of 100 pupils, only 50% applied to a highly selective university, 46 received an offer from a highly selective university, and 30% progressed to the highly selective university. These control groups were matched based on GCSE attainment and socio-demographics. A bit more detail here. This was a UCAS analysis based on 242 pupils who completed the Scholars Programme as Year 12 pupils in summer 2017. And these control groups were based on 500 groups of similar size matched by UCAS for GCSE attainment and socio-demographics. So basically the baseline is that pupils who complete the Scholars Programme are 26% more likely to progress to a highly selective university, or nearly twice as likely to progress to a highly selective university. Looking at the data, looking at a year of data, for example, we can see progress, namely in their academic achievement. This is based on more than 8,000 pupils who completed baseline, which is an assignment set at the start of the course, and then final assignment, which is set after 6 tutorials. Importantly, these marks are awarded according to a university style mark scheme to kind of show them how university works. So for example, 2 1s and firsts and 2 2s, etc. The 3 academic skills that are measured and focused on in terms of progress are written communication, subject knowledge, and critical thinking. And there's definitely progression in all of them. And importantly, we also aim to teach deeper learning skills that are important for university and they may not have had to delve into in school up to their in their school careers so far. These results are based on pre and post program survey responses of more than 7,500 pupils. Just to say a bit how it works, pupils place themselves on a scale from 1 to 7 for different statements. And the deeper learning skills that are measured are metacognition, motivation, and self-efficacy. And there's a bit of progress in metacognition and self-efficacy, which is good to see. This analysis was done by the University of Cambridge, who ran a randomized control trial, RCT, on the effect of the Scholars Programme on these intermediate outcomes, the intermediate outcomes being written communication, subject knowledge, critical thinking, metacognition, motivation, and self-efficacy. The Brilliant Club's use of data and research has evolved over time. It started off just being about reporting impact to partners, schools, tutors, universities, then evidencing the overall impact on progression to HE, higher education, then evidencing the overall impact on these intermediate outcomes, and understanding the differences in these outcomes for pupils. And recently, which is what I've been working on, finding ways to improve the impact of our programs. Just want to give here an overview of our data. We have lots of data on pupils, their age, gender, school year, ethnicity, and then targeting information on them, such as IDACI, which stands for Income Deprivation Affecting Children Index. It's basically a measure by postcode of how deprived that postcode is. Polar 4, which is a similar postcode level measure, but this one is specifically about progression to university. So that IDACI is a bit more general in terms of deprivation, and Polar 4 is specifically about progression to university. There's information on whether the pupil has any parental history of higher education and whether they have pupil premium status, which just means are they on free school meals. Then lots of data on the pupils' outputs, their participation on the program, their tutorial attendance, their baseline assignment scores, and their self-evaluation surveys. Those questions about those 3 intermediate outcomes that I showed you before, and whether they have received data sharing permission from their parent carer on things like more sensitive things like ethnicity. Also lots of data on the schools, their geographic data, which region of the UK they're in, the social mobility index of the area, whether they're classified as rural or urban, and some information about the tutors. And the only piece of information about the tutors I've used in my model that I'll get to is gender. There is more information about the tutors, but wasn't used in this case. So what I was trying to do during my placement was increase the number of pupils who successfully complete the Scholars Programme. And why is this important? The final assignment is what pupils work towards in their tutorials with their PhD tutors. It's a really big deal for them. It's probably the longest piece of work that they've ever written. And it's for sure, well, it's intended to stretch them beyond what they've done at school. So it's probably the hardest. And it is an excellent preparation for university. It's a university style assignment. You can see here on the right how important it is to some of the schools that have taken part, and how proud they are of their pupils who finish. But the problem is about 12% of pupils didn't submit their final assignment last year, meaning they didn't complete the program or graduate, meaning they didn't, they weren't able to put it on their CV or UCAS application. And some universities offer a reduced, better way to put it, some universities give a reduced offer for pupils that have completed the Scholars Programme, and more universities are clocking on to the fact that it's an excellent preparation for university. And like I've shown about 5 slides ago, we've got good evidence of the programme's impact on TSP, the Scholars Programme graduates. So what can we do to drive final assignment submission? Well, we've got a rich data source. Makes sense to talk about data. More than 70,000 pupil records, a yes, no, whether they've submitted their final assignment, and plenty of these variables that I've mentioned 2 slides ago, the pupil demographics, the pupil engagement data, school level information, and tutor level information. So the question was at the start of my placement, could we do the following? first of all, understand the factors associated with not submitting, and then create a prediction model that assigns a risk score to individual pupils, split into two different models. Model one, based on data we have before tutorial one, so before they actually start the program, and then model two, data we have after tutorial three, so basically halfway through the program, because there are 6 tutorials. The first one being intended to give some sort of early risk score, and then the second one being with a bit more information, so hopefully a bit better understanding using data, starting to understand how much they're engaging on the program. And then identify actions to drive the submission rate up. Whilst I was in conversation with the program team, the ones organizing and delivering the placements. And really importantly to me was to set this up in a way that could continue to be used. In my first placement with the NHS, I did some cool things, but I almost did too many things, and I wasn't able to, or I didn't have time by the end to set them up in a way that, let's say, a non-data scientists could continue to use them. And that's the environment I found myself in at the NHS and here. I was basically the only one that would do like machine learning stuff. There were other people that could do maybe data analysis stuff, but maybe not machine learning stuff. So that was my main goal for this, was to set up in a way that could continue to be used when I'd finished. So I'd really, if you were to host a placement, I would really emphasize that that's crucial, is to have things set up in a way that it can continue to be used after the student has finished. That might be obvious to you, but I thought it's worth emphasizing. Okay, so the first question, which factors are most important in predicting lack of submission? I'm not going to ask you to turn your head around, so I will list the top ones here. I've gotten this through the variable importance or feature importance of the machine learning model I made. First one is whether they completed the pre-assessment, that survey of their metacognition, motivation, and self-efficacy. Second, whether they received data sharing permission, which is very interesting because this is basically a proxy for have their parents or carers engaged, and engaged pretty minimally, to be honest, but engage enough to read a form and then sign it. So the first one is kind of like, has the pupil engaged, and the second one is that has their parent or carer engaged. Then, so the first two were on a pupil level in purple, the third one on a placement level in pink. The percentage of pupils on a placement who completed their pre-assessment. Just need a sip of water. Fourth one being the pupil year group. The older the pupil, the less likely they were to submit their final assignment. So the Brilliant Club works with pupils starting from year 3 to, really change that perspective about university early on, up to year 12, or the year just before finishing. Let me rephrase that in terms of age. Year 3 is, I think, 7 years old, and year 12 is 17 years old. And I don't know, I guess 17-year-olds are just getting more busy than 7-year-olds. On the graph here on the left, I've got an arrow that points up if it was correlated with submission. So, for example, if they'd completed the pre-assessment, they were more likely to submit their final assignment. But pupil year group here, as pupil year group goes up, the final submission goes down, anti-correlated if the arrow is going down. Okay, the fifth most important variable I found was pupil premium, which is this one about whether they're on free school meals. And as you might expect, if they are on free school meals, that is a sign of disadvantage and makes them less likely to submit. And the sixth one is, again, on a placement level, the percentage of pupils with parental history of higher education, with that being correlated with final submission. Also thought it was interesting to list some variables that were found to be unimportant, i.e., I guess you can think of it as not very correlated with final assignment submission. One of them was Polar 4, this postcode level index of university progression. The second one being whether the pupil had the same gender as the tutor. That was found to be unimportant. And third, the subject of the placement. So for example, I said I would be doing like I would do a STEM placement. There are also arts, humanities, social sciences. So I guess that was good to find that there was no bias towards any particular subject of final assignment submission. There were also some categories of categorical variables that were found to be unimportant. One of them being whether the pupil's gender was male or non-binary. It was sufficient information just to have a yes/no whether the pupil's gender was female. And if the pupil's gender was female, this drove the final assignment submission rate up. Second categories that were found to be unimportant was when the region was not England, so Wales, Scotland, or Northern Ireland, when the region was west or south, leaving just some importance for the region was North England, this is, and that drove the final assignment submission rate down. Whereas if a yes/no whether the region was east drove it slightly up. Most of the rural-urban classifications were found to be unimportant. So rural, urban with town, and urban with minor conurbation unimportant. Even just a little bit of importance for the kind of like most urban one, the urban with major conurbation, driving the rate slightly up. Yes, maybe because they might have a university nearby and know a bit about university. And something else found to be unimportant, whether the tutor's gender was male, female, or non-binary, leaving just some importance for when they wrote that they'd rather not say. So results now, I guess those were also results, but going into a bit more detail. Like I said at the start, I mainly use neural networks in my particle physics work. So from the start of this placement, I was like, oh, great, I'll just use a neural network for this. But when I was looking at overtraining or overfitting, this is what it looked like. And the fact that the blue dots are very far from the blue bars and the orange dots are very far from the orange bars was telling me that there was some overtraining. I think this was because the neural network was just being asked to learn too many variables and couldn't deal with it. So I then went on to try different algorithms. When I went to gradient boosted decision trees, it was better. In this case, the dots were close to the bars. So it wasn't an indication of overtraining, which meant I could trust the results from this algorithm, and those were the results that I showed over the previous slides. In terms of making a metric whether I was getting accurate predictions, I looked a lot at rock curves. I looked at other things as well, but based it on rock curves because there was some previous work in this domain of predicting risk in these sorts of education settings, and this organization called DataKind which is a really cool organization, said that something about 70 to 80% will be good enough to accurately predict pupils' probability of submitting. So when I was getting 81%, or 81 in the ROC curve, I was happy with that. A bit of detail about the model I made now. So I used previous terms with a known outcome to train the model, so supervised machine learning. What I did was, this was a bit arbitrary, but the team, the program team, they very much favored a kind of like high, medium, low risk, as opposed to a just, we think they won't submit, we think they will submit. Because they use that in other parts of their work, a kind of like traffic light, red, amber, green scoring system. So I thought that was very much worthwhile, just to increase the chances of this work being taken under their wing, you know, doing something that they're kind of used to. So anyway, I defined high risk as the area on this graph where the didn't submit was higher than the did submit. So everything to the left of that, where the light green is just above the pink. And low risk of not submitting, everything to the right of the peak of the pink, and medium risk in between. Like I say, this was a bit arbitrary. Could have maybe chosen other things. And then applied that prediction to the term that was ongoing when I was doing my placement, autumn 2021 to 22. It was really cool to be able to deal with currently incoming data and applying my model to that. So yeah, applied it to terms with unknown outcomes because the term hadn't finished yet, which means I no longer have this color distinction between the green didn't submit and the pink did submit. But I kept the same thresholds as the previous graph. And I would say, maybe you agree, they look somewhat reasonable on this graph as well. Everything to the left of here being high risk, everything to the right of here being low risk, and everything in between medium risk of not submitting. This meant that I could write predictions for each pupil. Oh, didn't mean to do that. And to help disseminate it to the teams, for example, make a spreadsheet that was ordered by the pupils that were at highest risk. And these columns were just for information to them, whether they completed the pre-assessment, whether they had that data form from their parent or carer, and whether they were on free school meals, pupil premium. The idea here being that they could go from the top, look across, have they completed their pre-assessment? No, so we really need to push that pupil to engage. Have they had their data form from their parent carer? No, we need to chase them up to get that, or chase their parent or carer up. And there's always this particular focus on pupil premium or free school meal students, because that is the main indicator of disadvantage in these sorts of contexts. And then I could kind of filter these per pupil predictions into a per placement prediction, and doing that by counting the number of high, medium, or low risk pupils per placement, and then order this spreadsheet by the number of high risk pupils per placement. Similar things here, counting the number of pre-assessments completed. So for example, they would deal with the first row first and be like, right, let's get on to that, the teacher of that placement or the tutor of that placement, and push them to encourage everyone to complete their pre-assessments. Similar story for the data forms. And again, for the pupil premium, just wanting to really push for placements that have a high number of those. This NCOP column is a yes, no, whether that placement is receiving extra funding from this organization, NCOP. And it's been found that if they are receiving this extra funding, they tend to be less engaged. The thought process behind that being, if they've kind of done it off their own back without this extra funding, they'll be more engaged. And then I've put this last column, cluster, which is geographical separation that the Brilliant Club uses, like East, West Midlands, so that they could use this column to filter and then focus on ones in a particular region if they needed to. Like I said, I thought it was very important to make this in a way that could be reproducible by, let's say, non-data scientists. So I put this in a data science pipeline called Data IQ, Data IKU. I do recommend this if you need to make a sort of data science solution accessible to non-data scientists. So everything is in here. The initial cleaning of the data sets, that is some calculation of extra variables, some joining, some filtering here. Then the split into current terms, or that says previous terms and current terms. Then the training of the two models, like I said, the one being on data before tutorial 1 and the second one being on data, well, including data from before tutorial 1, but also including data from the first 3 tutorials. And then some extra cleaning at the end to just give the risk scores. Now, the idea here wouldn't be to run both of them at the same time. The idea would be to just run the whole thing and only read the ones from the one that's currently needed, i.e. if the risk score is needed for the pre-tutorial 1 thing, i.e. tutorial 1s are going to start next week, for example, then would just read the one from there, or if we're halfway through the tutorials, read the one from there. Going towards my conclusion now, I want to say how this is being used currently and since I've left. These risk ratings are being updated each term for new pupils. The one for this term now was a few weeks ago, so it's exciting to see it being used, even though I finished. Using this reproducible data science pipeline. So now the placement organizers know which pupils need most support to submit their final assignment, which means they can inform the teachers which pupils need the most support, can inform the tutors which pupils need most support. There's also some written guidance being prepared on supporting the most disadvantaged pupils. I just want to also say a bit more about working with the Brilliant Club in terms of data science. There's, like I said, this amazing organization called DataKind. That's about volunteering some of your data skills for mission-driven organizations that improve the world. The Brilliant Club is just one of them. You could help many other organizations. So if you've got some time as a data scientist, you can do that. Some organizations, maybe yours, you might have some company days where you're free to work on whatever data problem you want. Thank you, Colin, for your message. And if you're interested in either of these or have some other idea in which you could help the Brilliant Club in terms of data science, then we're very interested to hear. Just email hello@thebrilliantclub.org.